Okay, welcome everybody to our webinar, Sample Weighing for Fusion and XRF. My name is Rainer Schramm, and today I would like to give you an idea about how precise do you need to weigh to do fusion for XRF, for X-ray fluorescence analysis. So my presentation is about X-ray fluorescence. So shortly I will explain the procedure. Then I picked the sample preparation fusion because this is the one where we need the highest precision in weighing, because it's also the technique where we expect the highest precision from the analysis, and that's why you then have to take care the most for preparing the sample. So we talk about weighing, what are the general influencing factors, and of course we have to think about where is our error of analysis coming from, and in this way we can adjust then our work steps. Also, I would like to present you the real errors in the laboratory, and we shortly also talk about automatic weighing for fusion, and of course a conclusion in the end. Yeah, generally, if we do XRF, we have, of course, our sample, and to measure it in the XRF instrument, we need to prepare it. And in the end, we get our result. So this is the classical workflow. And sample preparation in XRF means mainly weighing the sample and weighing the additives. Like, for example, in fusion, we have to add a flux to dissolve the sample into it, or sometimes, if we have, for example, slags or ferroalloys, we also have to add some more additives like oxidizers, and also there we need to weigh them. And for every weighing step, there is the real question, how precise we have to weigh this to get still the best out of our XRF method. And this is what I would like to talk about today. So fusion, shortly, how does it work? We have our sample and we mix it with a flux. And mixing means really that you have it well homogenized before, so that you have the maximum contact between sample and flux, so that it dissolves then when you put heat on it as easy as possible. Once it's all getting liquid, then the liquid has to be agitated, and in the moment it's homogeneous, you could pour it into a preheated mold in expectation that also the glass is homogeneous in the end. And last but not least, finally, you have to cool it down to avoid any cracking and to get also a stable homogeneous glass. So if we now look where are weighing steps in this procedure, then of course we have to weigh a sample and we have to weigh the flux, and both result in a dilution factor. So it's not only the dilution, it's not only the weights of the sample and flux, it's also the dilution what counts. Additionally, we could weigh the empty crucible, we could weigh the crucible after pouring, and this of course will tell us something about how much material was left in the crucible. And if we then also weigh the fuse speed, then from all this information, we could also calculate a loss on ignition of the whole process. Some people are doing this. This is why I just wanted to mention it here. But let's think about, we have a glass bead. And the glass bead was made from a dolomite, a dilution ratio 1/8. So 1 part sample, 8 parts flux. And then the main question is, where is our information coming from in the bead? And for this, I just mention here the penetration depth for different elements. And you see that with increasing atomic number, the penetration depth is going up. And for example, for potassium, we will have a penetration of something around 80 micrometer in the bead. But this means that if the total mass of that bead varies, it doesn't matter about the result for potassium, because the information of potassium is only coming from this volume here. And that means if here the thickness changes, it has no effect to our final result. So that's the first very important question or information, that for some elements, they are measured only from the surface, like sodium, and then with increasing atomic number, we go deeper and deeper into the bead. And of course, there will be a certain limit, let me say after 2-3 millimeter, when we have X-ray then the complete bead, where then suddenly the thickness will also count. But in the end, we have to think about an analyzed volume, and this means that dilution here is important, but not the absolute mass. So if we just take this potassium example, it means that the intensity you get out of this volume, you will then just correlate with your calibration curve to a concentration, and this concentration then is depending on the dilution factor, which then is calculated out of the sample you weighed and the flux you weighed, but it's the ratio what counts and not the individual weights. But the other really important point is the error we see in the real world is the inhomogeneity here in that volume. And you will see that this is much bigger than any kind of weighing errors. And so that the most important message here is you have to keep the dilution constant and not the absolute mass. But of course, this is only important when you do empirical calibrations. That means that you don't do any kind of theoretical correction in XRF, so that you calibrate your X-ray with standard materials, and you prepare them exactly in the same way than your unknown samples. You keep everything constant, also the mass and the dilutions. If you use fundamental parameters, this would allow you that you can vary the dilution factor and you can vary the mass, but you have to enter the exact figures that the software is able to calculate the effect out of it. Let's talk about the thickness again. Normally, I would guess that a typical fuse bead is something around 3 millimeter thick. And if we then measure our elements, for example, with K-alpha lines, then it's this red marked elements where the bead will be infinitely thick. So here you don't need to take into account the bead thickness. If the atomic number is higher, you will see, like for strontium here, you will see that the K-alpha line is really varying with the thickness of the bead. So you get a much bigger spread of your points in calibration if you would use the K-alpha line. If you then instead use the L line, you will see that you come back to the same performance than these mentioned elements. So that's the rule. Up to bromine, you can use the K lines, and then from rubidium on, you have to use the L lines to be always on the safe side that the total mass of the bead is not counting. Okay, let's talk about weighing. If I install a balance in my laboratory, I need to make sure that it's leveled, that the weighing table is absolutely stable and no vibration from neighbor instruments or from the room itself can affect the weighing. The working area is important, so what room you're using, and of course also the altitude you are, because this will change the weight the balance shows you. Temperature is an influence, moisture, and light. So if you put it in front of a window and the sun is shining on your balance, this will also change the performance. And of course, any airflow in the laboratory, for example, from an air conditioning, will definitely influence your quality of weighing results. But that means all these points you have to get under control so that finally the weighing error is not really important for your X or F measurement. But another point which is important also for automatic weighing system is electrostatic effects. So what happens there? When material is running down a slope or is touching a wall, and this then leads to a charging of the particles. And if they are charged all the same way, then Yeah, they don't like each other. They just want to go out, and this makes the whole product more heavier than it is. So your balance will show a higher weight than in the real world. And this is especially the case when the humidity in your room is below 40%, because then these particles have no possibility to discharge over the humidity. So this is why it's important that the humidity is kept in a range of, let me say, 40 to 60%. My personal experience, what I saw is that the error could be in that range, about 4 milligram if you weigh 8 gram, which is just an empirical result from my experience. This is what I have seen on statical charged materials. So you have to know that to avoid this, you could use everything from metal. So if you use a metal crucible, then this will discharge the particles immediately. Glass is also okay. Plastic is not good. Out of you use conductive plastic. So there are some special um, weighing boats which are made with an conducting plastic. Then it's also okay. Also, humidity plays a big role, and there is also some kind of ionization tools where an airflow is coming to your material, which is charged in plus and minus, and so these particles always will find another charging to finally discharge the particles, and then the weight will be correct. Yeah, so this is something you really have to take care, especially if you use glass vials or plastic weighing boats. Okay, I just went into my laboratory and looked on our metal balance, and this is the sheet I got from the calibration. So here you see that this is the main formula, which shows me the weighing error of my balance. Yeah, here in bigger scale. So you see there is always an absolute error, which is always there. And if I then multiply with the real weight, then I get the total error. So you can see it here. From very small weights, it's always 0.17 milligram. And then for higher weights, an additional error is added. And for our flux weights, like 8 gram, this will be in the range of 0.3 milligram, or for 1 gram sample, it will be in the range of 0.2 milligram, so very low. So this is probably not the error you will see in your laboratory. That means if the balance is installed under optimal conditions, then the weighing error is really small. Make sure that the calibration you get for a balance is always made at the location you use it. If you move the balance, the calibration is gone and you should have a new one. This is always important to know. So the second source of error is our XRF. So let's see what is there the error. So I took one glass bead and I measured it 10 times. And you see the standard error I get is 0.07%. And this means if I transfer this to my weights, a 1 gram sample, this will be 0.7 milligram, or for the flux is something around 5 to 6 milligram. Yeah, so this is just that we have a feeling of how much error would it be converted into weighing a sample. If we look in some standard norms, like the cement norm, they also mention what is the performance you should achieve so that you get for a certain concentration, what is the precision you should have. And this means this is the maximum error which is allowed in our method. So it means then, of course, all our weighing errors should be below that. Otherwise, we cannot achieve this performance. And here you see that if I have a cement with 65% calcium oxide, then I should achieve something like an error of 0.235%. And if I convert this again to my weighing 1 gram sample, it would allow something like 4 milligram error, and it would allow already 29 milligram on the flux weight. Yeah, if that means this is exactly the error which is still in agreement with the method used. Now let's see how this works in the real world. So what did I do? I weighed a sample exactly 1 gram and flux 8 gram. And now I really increased the weight for my sample to see how the result is affected. And what I also put in here is the blue line is the given value. So this is the certified value I should achieve. And the red lines, this is what the method tells me I should achieve as maximum error. And that means the first sample, which is perfectly weighed, this is this point. So it's a double preparation, and I show you the mean value. And you see now I increase my sample weight. This is then this at 0.2 milligram more, and 4 milligram more, 6 milligram more. So you see this is still, all are still inside the error, but then with 8 milligram I'm out. So you see that in a certain way, it allows me to make an error in weighing without affecting really the final result. And you see, this is the one from the sample. If I would change the flux, I could increase up to 30 milligram error without leaving here my error range. Another view to this kind of error is I have a control sample in my laboratory. It's a cement. I measure it 1 year. And of course, I have my mean value. This is the black line. And I get my error from the laboratory, which is the red line. This is 3 sigma, the precision of this control sample for calcium oxide. And of course, it was always weighed perfectly on the balance, 8 gram flux, 1 gram sample. But of course, the error I see here, I could also convert into a weighing error. And then you see this is about 4 milligram for the sample and about 32 milligram for the 8 gram flux. And there you have a feeling how the real error in the laboratory, and this is what is it? It is inhomogeneity in our beads. It's the variation from one fusion process to the next. It's the sample measurement error, and of course also the weighing error, all collected. And you see this is much more than what my balance really allows me. Another point or investigation I did was I checked how the additives, like an oxidizer in a slag method, is affecting the final results. So what do you see here? You see here a slag sample, which is 0.5 gram, and the flux 8.5, so they were weighed together. And the values for the exact weighing was exactly here for the given value. So this is the given value of my slag sample and for calcium oxide, and this is the classical laboratory error we see. So all these weighings are inside the error. And what did we change? We changed now the oxidizer. We use strontium nitrate. We add to the slag and the flux. And my question was, how much can I vary in the weight of strontium nitrate without affecting my final result? And this is quite interesting because you see here that that we can vary up to 2% in our 1 gram additive without leaving really the error range of our analysis. Yeah, so you see here, this is here 2%, and only when we go higher to 2 and 4%, then we are out of the precision limits. Yeah, so this I think is quite interesting, especially for automatic dosing systems, that such additives we don't need to add very precise without affecting the result. And then if I transfer this to the classical weighing errors, this is very high. Okay, let's put together now a bit our error budgets. So first of all, we have our target. This is we want to weigh 1 gram sample. We want to weigh 8 gram flux. And of course, we have a dilution factor then of exactly 8. The balance We'll just add a very low error of 0.3 milligram, 0.2 milligram flux ensemble. And of course, also the dilution is just yeah, 3 4 digits after the comma. What about XRF? Error is already a bit higher. So here we are in the range of 6 milligram and 0.7 milligram. If we look now on the sample preparation, then we see this is our real error. Yeah? So it's much higher. And also the dilution shows a much higher error. And so the question now is, if I train my lab people, how precise they have to weigh so that this final error is not effective, because this is the error we get anyway, yeah, which is not part of the weighing. And so our recommendation is that you should be in a range of 0.1% relative for flux and sample, so that then if both adds and vary, you have 0.2% error on the dilution factor. So you are still half of the preparation error you will see anyway. Yeah? So the rule is keep your weighing error 2 times lower than your preparation error, then you are still good enough. But it has no influence to your final result. Now let's have a little bit of look in direction of automatic weighing systems, and that means we want to use now this fact that a weight could also vary in a certain range, and there we have to think about the catch weight procedure. So what is this? If you really want to do a fusion and you expect a dilution factor of 8. So you weigh 1 gram sample and 8 gram flux, ideally. You could also weigh 10% more, 1.1 and 8.8. The dilution is still the same. And remember, it's the dilution what counts and not the absolute mass, which plays a role. Or you could do also 10% less. That means you weigh 0.9 and 7.2 and still you have a dilution of 8. Yeah. So the concept of catch weight means keep your dilution constant, but to make life easier, you could vary your sample weight. You just have to make sure that the flux you weigh is then just exactly in the ratio of 8 to your sample. Of course, there are limits. You cannot make your crucible too full, because then your mold will be overfilled and you get spillage. Or if you have not enough material, then you get such called half moons in your mold. And then, of course, this also makes no sense. So catch weight in our automatic system means that first we weigh a bit flux, so that our sample is not really at the bottom of the crucible. And then in a second way, you put sample, just roughly between 0.9 and 1.1 gram. So therefore you use such a small balance just to estimate your amount of sample. And then when this is done, it is weighed on the precise balance again, and the software is calculate how much flux you have to add that your dilution factor is exactly 8 in the end. Yeah? So the concept is first dose a bit of flux, then the sample by the user, and then complete the flux dosage so that the dilution factor is exactly 8. So in the reality is the machine is doing the first layer of flux, then the user is adding the sample, and then the machine completes the job. Yeah, and this you can do up to 30 samples in total. But of course, also flux properties play a role. First, we have to get the moisture under control, and there you have to know that crystalline flux takes much more moisture than the glassy flux. And for the dosage, it makes a difference if you have granular flux, where you have unshaped particles and they could stick together, or you have spherical beads, which every particle just rolls like a ball, and then can be dosed, of course, much better. In the end, it counts for automatic dosing systems what is the weight of 1 grain. So for example, our spherical flux, one particle weighs 0.1 milligram. So that means I have always the precision if I dose particle per particle to get whatever the user wants to have. If the grainy flux sticks together and one lump is already 1 milligram, then of course I can only have a precision of 1 milligram and not lower. This is something you just have to know to understand how the precision in a flux doser is working. Let's see how it works in the real world. For example, if we say to the Boramat dose 8 gram, and this is the precision we allow, then the machine, of course, is able to do that. Of course, the point is, do we need that kind of standard deviation in the end? And no, because what we learned today is that, let me say, 8 milligram would be absolutely acceptable without affecting the performance of our systems. And that means that you can gain time. That means you could say the Boramat, yeah, for the dosing error, you can increase it to 8 milligram. And then, of course, the machine is much faster in comparison if you want to have really the best of the best. Here, just an example, also manual weighing, automatic weighing. So normally there should be no difference in as long as you adjust the machine in a way that the error is low enough and you give the machine time to fulfill the precision. Okay, conclusion. Conclusion means, first of all, you have to make sure that your balance has ideal conditions so that the balance error in the end is not counting. Yeah. The second is you have to understand where the error is coming from. And I think today you learned it is coming from the sample preparation itself. That is the highest source of error. If balance works optimal and your XRF, of course, measures under optimal conditions so that also the weighing, the measuring error is negligible like the weighing error. And finally, you have to define for your laboratory, what is my weighing target? What is the error I allow to my people to weigh on the balance for the sample, the flux, and any kind of additives I need for my fusion process? And normally automatic weighing does a very good job by helping the people to get some more free time they can use then for other things like calibrating XRF or other laboratory jobs so that there is more capacity in the laboratory. Okay, thank you so far. This was my webinar about weighing, and now I'm happy to see some questions from your side. So here is one question. What diameter fuse speed are you using? I would always recommend to use 40 millimeter. And the main reason for this is that the surface you use then in your cassette that your bead is laying on, this is then giving the lowest error. You can estimate as smaller your bead is, and your cassette has to be then also smaller, then the margin your bead is lying on the cassette is very little. And as smaller that is, as higher is the error only from the positioning of the bead in your cassette. This is why I always recommend to use 40 millimeter beads, because then only from that fact that it's a bigger diameter, the error is lower. Okay, any more questions? Can automatic weighing be done also on wax for press pellet, or is it working only with flux for fuse speed? So the Boramat like we use it today is only working for fuse speed because it's the flux which defines the performance of the machine. The wax will be too sticky for that kind of machine, but there in future also possibilities are available, but not for the moment. Any more questions? If there are more questions, you can always send us an email. We are always happy to answer this. So here is how about direct fusion versus ignited base. An ignited fusion always has, or ignited samples always have the advantage that you have no loss on ignition during the fusion process. And this, of course, is also a source of error. Yeah, that means that ignited samples have the advantage that they sum up to 100%. So you have another possibility to control the performance of your fusion process. And another advantage is that calcine samples do not attack the platinum ware so much than if you do direct fusion. Yeah, direct fusion means that you have a loss during the fusion. And there could be, of course, if there's a high loss, also some spillage out of your crucible. And these are then typical sources of errors. Then there's another question. Any advice on metallic samples? For weighing, yeah. If you do ferroalloys, then of course you have first to weigh your sample, which is very little. So you have to be very precise. And what I would use is a weighing boat together then with the oxidizer. So you weigh your sample, you weigh your oxidizer, perhaps a catalyst, you mix it, and then additionally use your crucible, you weigh there your flux, and you put then the mixture on top of it. So this is the way I would weigh any kind of metallic samples, which have to be oxidized then in the first fusion step. Any more questions? Okay, like I said, if there tomorrow you have another question, just send me an email and I'm happy to answer this to you. And so then I hope that I could give you some new insights into weighing where is the error really coming from. And perhaps you save some time because you don't need to weigh every sample very precise, only just as precise as necessary. Okay, then I thank you very much for listening and I hope to see you again in any of the next webinars. Thank you very much. Bye-bye.